The historical record of electrical generation technology contains multiple examples of systems that demonstrated technical functionality in controlled environments, but never achieved commercial distribution to residential consumers. Between 1890 and 1970, at least 24 documented energy conversion technologies progressed through prototype stages, laboratory validation, and in some cases limited field deployment, yet remained absent from the consumer market that developed during the same period. This pattern reflects a consistent disconnect between engineering viability and market accessibility. A technology might successfully convert one form of energy to electrical current in repeatable laboratory conditions, receive patent documentation, and even operate in specialized applications while simultaneously failing to reach general household adoption. The factors determining market penetration operated independently of the technical performance characteristics that defined engineering success. The technologies examined here represent documented examples where this disconnect is particularly clear. Each achieved functional demonstration. Each addressed the fundamental task of electrical generation through distinct physical principles. None transitioned to widespread residential use during their development periods or in subsequent decades. I'm James Sullivan. Let's examine 5 specific examples from the historical record. Atmospheric electricity collectors, 1890s to 1920s. These systems operated on the principle that electrical potential exists between the Earth's surface and upper atmosphere. Elevated conductors, typically metal rods or wire arrays positioned on tall structures, accumulated charge differential that could be drawn off as current. Multiple inventors, including Nikola Tesla and Hermann Plausen, developed functional prototypes that demonstrated measurable electrical output. The technology faced 2 primary obstacles. Output variability correlated with weather conditions, atmospheric moisture, and geographic location, making standardized performance specifications impossible to establish. Additionally, no consensus emerged on optimal collector geometry, elevation requirements, or grounding configurations. Without standardization, manufacturers could not produce components for general distribution, and electrical codes could not incorporate the technology into building standards. Thermoelectric generators, 1920s to 1940s. Thermoelectric devices convert temperature differentials directly into electrical current through the Seebeck effect, discovered in 1821. By the 1920s, materials like bismuth telluride enabled construction of solid-state generators with no moving parts. These devices operated silently and required only a heat source and cooling sink to produce continuous electrical output. The limiting factor was conversion efficiency. Small-scale thermoelectric generators typically achieved 3 to 7% efficiency, meaning 93 to 97% of input thermal energy became waste heat rather than electricity. While this proved acceptable for specialized applications like remote sensing equipment, it could not compete economically with grid electricity or fuel-based generators for household power needs. Research into higher efficiency thermoelectric materials continued through subsequent decades, but never reached cost-effectiveness thresholds for residential markets. Electrostatic generators, 1930s to 1950s. Electrostatic generation, producing electrical potential through mechanical separation of charges, had been demonstrated since the 18th century. By the 1930s, devices like the Van de Graaff generator and Wimshurst machine could produce hundreds of thousands of volts for research applications. These systems generated electricity through rotating elements that accumulated and separated electrical charges without electromagnetic induction. 2 factors prevented household adoption. First, electrostatic generators produce high voltage at very low current, the inverse of what household appliances required. Converting this to usable power introduced complexity and efficiency losses. Second, high-voltage discharge created safety concerns that existing electrical codes and insurance frameworks were not designed to address. The systems remained confined to laboratory and industrial applications where specialized infrastructure could accommodate their characteristics. Radioisotope thermal generators, 1950s to 1970s. RTGs convert heat from radioactive decay directly into electricity. typically using thermoelectric converters. Developed in the 1950s for space exploration, these devices provided reliable power for decades without maintenance, refueling, or sunlight. Voyager spacecraft launched in 1977 continue operating on RTG power as of 2025. The technology demonstrated unambiguous long-term functionality in the most demanding operational environments. Regulatory frameworks prevented any pathway to residential use. Radioactive materials licensing, containment requirements, disposal protocols, and liability structures developed for industrial and government applications created barriers that no commercial manufacturer attempted to navigate for household products. The technology remained restricted to space programs, remote research stations, and specialized military applications despite its proven reliability. Induction-based energy transfer. 1890s to present, Nikola Tesla's experiments at Wardenclyffe Tower in Colorado Springs demonstrated that electrical energy could be transmitted through electromagnetic induction without physical conductors. Modern wireless charging systems for small devices operate on similar principles. The technology successfully transfers energy across air gaps using resonant electromagnetic coupling. The fundamental limitation is energy loss proportional to distance. Wireless power transfer achieves acceptable efficiency over centimeter-to-meter ranges, but experiences exponential losses at longer distances. Tesla's vision of transmitting power across miles encountered physics that made it economically unviable. The energy required to establish the electromagnetic field far exceeded the energy successfully transferred to receivers. The technology found application in short-range device charging, but never scaled to household or grid-level power distribution. These technologies shared common barriers unrelated to their engineering functionality. Existing electrical infrastructure had developed around centralized AC generation and distribution. Grid systems, electrical codes, appliance standards, utility rate structures, and installer training all assumed this configuration. Technologies operating on different principles, whether high voltage, low current, variable output, or alternative form factors, encountered infrastructure incompatibility regardless of their power generation capabilities. Capital concentration patterns also influenced adoption trajectories. Companies with existing grid infrastructure investments had limited incentive to pursue technologies that might reduce dependency on centralized distribution. Patent acquisitions by established utilities sometimes resulted in technologies remaining undeveloped. Independent inventors or small manufacturers lacked capital for the manufacturing scale, distribution networks, and regulatory navigation required to bring new electrical technologies to mass markets. Standardization processes created additional friction. Electrical codes evolved incrementally to incorporate technologies that fit within existing frameworks. Systems requiring entirely new safety standards, installation procedures, or appliance compatibility faced multi-year approval processes through engineering standards organizations, insurance industry review, and municipal code adoption. Technologies that demonstrated functionality but fell outside established categories often stalled at this stage. The cumulative effect was that market success required not just engineering viability, but alignment with existing infrastructure, compatibility with regulatory frameworks, access to manufacturing and distribution capital, and fit within consumer expectations established by decades of centralized electrical service. Technologies lacking any of these elements remained marginal regardless of their technical characteristics. The pattern documented in these historical examples continues in contemporary energy technology development. Multiple current technologies demonstrate functional electrical generation in research or limited commercial contexts, but have not achieved widespread residential adoption. Small-scale fuel cells, piezoelectric generators, microbial fuel cells, and various mechanical energy harvesting systems exist as functional technologies absent from typical household energy conversations. The same structural factors apply. Infrastructure compatibility, regulatory pathway availability, manufacturing scale economics, and distribution channel access continue to determine which technologies transition from demonstration to market presence. Technical functionality remains necessary but insufficient for residential market penetration. This creates a category of technologies that exist in documented form: patents, research publications, working prototypes, limited deployments, while remaining absent from mainstream residential energy options. The category has expanded rather than contracted over the past century as research has proliferated faster than regulatory and commercial adoption mechanisms have evolved. One format that exists within this broader category of documented but non-mainstream technologies involves electromagnetic induction devices using specific coil geometries. These devices appear in patent records dating to the 1890s, with various implementations developed across subsequent decades. Contemporary versions typically consist of wound copper wire in bifilar or pancake coil configurations, housed in compact enclosures. The format is distributed primarily through technical documentation rather than retail channels. Assembly instructions, component specifications, and wiring diagrams available as digital downloads or printed materials. Implementation occurs at the household level using components sourced from electronic suppliers. The devices connect to existing electrical systems through standard procedures and operate continuously once installed. This format represents one example among many technologies that exist in documented form outside mainstream commercial channels. Its presence illustrates the continuing pattern where technical documentation and functional implementation exist independently of broad market adoption. The historical pattern documented here, technical viability without commercial success, reflects structural dynamics in how energy technologies move from demonstration to consumer accessibility. These dynamics operate at the level of infrastructure compatibility, regulatory frameworks, and capital distribution rather than engineering performance alone. Multiple technologies from different eras and based on distinct physical principles demonstrate this same pattern. Their collective presence in the historical record establishes that the category of functional but non-mainstream energy technologies has existed continuously throughout the electrification era and persists in contemporary form.